Hello, my name is Adonai Cruz. I am a PhD student at the Eindhoven University of Technology in Netherlands under supervision of Professor Michael Flatte. And in this talk, I'm going to show my project on the nanoscale structure of the orbital magnetic moment of a single dopant spin in semiconductor. The main motivation of this work is to study point effects in solids with highly localized electronic bound states. Such states are called deep centers and are promising candidates for quantum technologies based on spin. They can originate from a variety of defect types present in different substrate materials, for instance, magnetic dopants, diamond NV centers, or silicon carbide divacancies. They show specific characteristics that make them suitable candidates for spin qubits. The high localization of its wave functions makes them isolated from sources of coherence, for instance, nuclear spins. And secondly, the defect's excited state manifold allows the defect to be optically initialized and measured. So in order to coherently control them, an understanding of how these electronic states couple with external fields is primordial. In this project, we want to address the problem of evaluating the orbital contribution to the magnetic moment associated with these highly localized wave functions of deep centers. The origin of the orbital magnetization comes from the dissipation-less charge currents carried out by ground state wave functions, as done in quantum mechanics course. When you want to calculate the probability current, we can write an expression for the charge current like this. And since we are interested in ground states, there's no charge accumulation in the system. And as a consequence, by the continuity equation, it ensures that the calculated currents are circulating. So there are no sources or sinks since the current divergence is zero. As an example, we can look at circulating currents associated with hydrogenic orbitals with not null magnetic quantum numbers, ML, originated from p-symmetric states. So on the left, we plot the current vector field of the ML equals 1 wave function, showing its counterclockwise circulation, while for the m equals minus 1 state, as shown on the right, the current circulates clockwise. So in the analogy with classical electrodynamics, the circulation of the wave function has an orbital magnetic moment associated with, which points in the opposite directions for different values of m. And similarly to what happens with the spin moments, when an imbalance in the occupation of ML states occurs, a net magnetization is present in the system. And that's the orbital magnetization. So in order to obtain the electronic state of the defect, in this work we employ a Coster-Slater time-binding formalism using Green's functions. It allows us to perform calculations of different kinds of point effects in a variety of substrates. For instance, we can look at single substitutional magnetic dopants like manganese, cobalt, or iron, or vacancies like divacancies in silicon carbide. And also a combination of vacancies and impurities like the diamond NV center, or study the interactions between pairs of defects. The strength of this method relies on the Green's function formulation from an empirical time-binding Hamiltonian that describes with high accuracy the pristine bulk material. And once we have calculated the homogeneous Green's functions for the substrate in real space, our method allows us to add different perturbations corresponding to different kinds of point effects, thus saving great amount of computation time and without the problem of supercell effects. Since the defects that we are interested on creates deep levels, the perturbation it creates in the lattice can be taken into account by short-range potentials that affect only the defect sites and its nearest neighbors. So in the Green's functions formulation, we can calculate the perturbation via Dyson equation, like in this expression, where the potential matrix V give us parameters to set the defect binding energies, as well as to resolve angular momentum and spin states. So to better understand the origin of the spin-correlated circulating current that we are interested in this work, we're going to study the substitutional manganese in gallium arsenide. So in order to look this, we have to understand the ordering of the electronic levels of a single transition metal ion in a tetrahedral crystal field. So here initially an isolated transition metal ion has a full rotation symmetry, and all of its 5 D states of the 3D are degenerate. But when it substitutes a gallium atom in the lattice of gallium arsenide, the symmetry is reduced to the electronic potential of the environment, and the D states are split into 2 corresponding sets of the 2 reducible representations called T2, which is a triple degenerate, and E, which is a doubly degenerate. So these are reducible representations of the tetrahedral TD point group. Furthermore, exchange interaction splits the spin components of both sets. And finally, only states with T2 symmetry hybridize with the dangling bonds of the neighboring arsenic atoms, giving rise to bonding anti-bond states, while the E state remains as atomic-like localized states without hybridizing with the lattice. So in our further calculations, we will focus on the anti-bonding T2 symmetric acceptor state, localized at 113 MeV above the valence band edge, with spin polarization along the 001 crystallographic direction. So in order to calculate the circulating current, we defined a current operator formalism valid for the time-binding Green's functions we have developed and calculated previously. This current is discrete and defined at each atomic position R, given by the vector R. And since our time-bind Hamiltonian includes only nearest neighbors, the current that has a dependence on the hopping terms summed over only the 4 nearest neighbors of the zinc bank lattice, as shown in the picture. In the right side, we have the plot showing the magnitude of the current evaluated at atomic positions. On the x-axis, we have the distance in units of the lattice constant of the gallium arsenide with 5.65 angstroms, and the distance is calculated from the imputed side. So as can be seen, the magnitude decays fast when we move away from the impurity, being already 1 order smaller already at the 3rd nearest neighbors. So this shows the localized nature of the circulating current that we are looking at. And from the circulating currents that we calculated before, we can calculate the associated orbital magnetic moments, mu orb, in this equation, and the corresponding dipolar magnetic fringe field. On the left side plot of the field, we plot the field for manganese impurity at the 010 cleavage plane of gallium arsenide, while at the right we have the field in the 001 plane. In both calculations, the spin polarization of the core is fixed along the 001 direction, is indicated by the red arrow in these plots. And as can be seen from both plots, the spin dictates the anisotropic shape of the field, showing the spin dependence of the circulating currents. With this result, we believe that the experimental magnetometry with nanoscale resolution, such as those already realized with NV centers and vacancies in silicon carbide, might provide a tool to distinguish the spin orientation of spin centers in solids. And with this, I would like to conclude my talk and highlight that we have developed a theoretical framework to calculate the spin-correlated circulating currents of localized states from point defects, and we have shown promising results relating these currents with the measurable fringe fields. Thank you.